อยู่ไม่ใช่เหรอ
Okay, so now it's already 2 p.m. So I would like to start the webinar. And today is the KMUTT Carbon Neutrality by 2040 webinar series number 4. And this afternoon we have an invited speaker, Professor David Werner from School of Engineering, Newcastle University in UK. Professor Werner is currently a visiting professor to KMUTT under the project on sustainable aquaculture within peri-urban green infrastructures protecting the Gulf of Thailand from eutrophication, supported by Biotechnology and Biological Science Research Council. The project is in collaboration with Dr. Soida Vinit Nantarat from the School of Energy, Environment and Material. For the webinar today, he will share with us his research experience in method development to analyze terrestrial carbon stocks, including soil and tree biomass, for credible carbon offsetting strategies in institutional land. The title of this talk is Offsetting University Carbon Emission in Research Farms. This webinar is timely since the topic is of interest by various organizations and individuals, as well as KMUTT, having their commitment to carbon neutrality by 2040. Without further ado, I would like to invite Professor to give his talk. So Professor, the stage is yours.
Thank you. So can you hear me via the microphone?
Yes, but I think it's your voice is a little bit small. Is it possible to move the microphone a little bit nearer? Yeah.
Yeah, right.
Yes, thank you.
Okay,
Great.
that's better. Yeah. Okay, so thank you very much for this invitation. And I quickly skip to the second slide because the title is not correct. So today I would like to talk about the work we did to assess opportunities for offsetting the university's carbon emission at our research farms. So my talk will have 4 sections. First, I give you the context. Then I talk about our methods. Next, I will show you the results, and I will end with some conclusions. So universities are emitting carbon dioxide and quite a substantial amount of it. So in the United Kingdom, the universities are responsible for about 3% of carbon emissions in the United Kingdom. And that's a similar number in the United States. It's about 2%. So like you mentioned, that KMUTT declared a net zero target, the same we did at Newcastle University. So in 2019, we declared a climate emergency and pledged to reduce our Scope 1 and 2 emissions by 2040. Last year, this target was actually brought forward, so I should have said in April 2021. So we now pledge to reach net zero emissions by 2030. So that is really ambitious because that's just 8 years from now. So 8 years from now, the university wants to reduce its carbon emissions to zero. I don't know if this will work. So this is just the YouTube video from the universities where they kind of promote their carbon strategy. And I don't know if you can hear it, maybe not. Do I need to unmute my microphone? Sorry. Should I unmute to play this? You must have sound. This one. Oh, okay. Great. Glad you're here. Let's hope this works now.
Here at Newcastle University, social and environmental justice is a core value, and we're committed to embedding this in all aspects of decision making.
Drawing on our expertise and strengths in research, we are working collectively with colleagues, students and stakeholders.
In 2021, recognising the urgency of the challenge, we brought our net zero target forward from 2040 to 2030, and we're committing £15 million per year towards delivering our climate action plan.
We are approaching this target with bravery, honesty and urgency, and believe our 10-point plan will help us reach success. Over the coming years, we will decarbonise our power, heating and cooling, and enhance self-sufficiency through on-site renewable energy, reduce energy usage across campus, reduce energy used for construction as well as for IT infrastructure, minimise carbon emissions associated with purchased goods and services, establish and promote sustainable travel, reduce emissions linked to our investment and endowment funds, reduce waste, reuse all we can and increase recycling, embed social and environmental justice in research and education, be a leader in sustainability and provide support to other organisations, raise awareness of climate amongst our students and colleagues.
The journey to net zero may seem daunting, but it is an absolutely crucial one. Together we can protect the planet for people everywhere, future generations and the natural world to thrive.
Okay, so this is the pledge from the university, and it's a very flashy YouTube video, and you probably will see similar videos for different universities. So maybe to clarify what we want to offset, or for which type of emissions we want to reach net zero, these are called Scope 1 and 2 emissions. So Scope 1 emissions are emissions that result from the use of institutional cars, vehicles, and also from any power generation on site. So these are the direct emissions from the university, from the use of its vehicles and facilities. Scope 2 emissions are related to the electricity, heating, or cooling that we are purchasing from outside providers. So these are the type of emissions that we want to bring to net zero in 8 years' time. It does, for example, not include my trip here to Bangkok. That would be scope 3. So it's just important to know that what we are talking about is emissions from vehicles and facilities of the university, or purchases of electricity, heating, and cooling only. So here's an overview of the scope 1 and 2 emissions from Newcastle University and how this has changed over the last decade or so, or a little bit more. So you can see in pink here, these are the great electricity emissions. So these are the emissions from the electricity that we are purchasing for the university. And you can see that for these electricity linked emissions, we've seen a substantial decrease in the last 5 years or so. So that's relatively easy to get rid of. You can just purchase renewable electricity generation. So reducing these sort of emissions is relatively straightforward. Or you can install solar panels, you saw that on the video, or you can try and have biomass generated electricity and so forth. Or you saw the electric vehicles. But what you can also see in this graph is the blue bars here. So this is the purchase of natural gas, and that's mainly for heating our buildings. And you can see there's hardly any reduction in these emissions that are linked to the purchase of natural gas. And then some of the other emissions, they're much less, so they're basically insignificant. So we have 2 types of emissions that are making up the main bulk of our emissions, which both are linked to the purchase of electricity or the purchasing of gas to generate heat, to heat our buildings. Now, I would argue, if you look at the trend here for the natural gas consumption, I can't see how by 2030, in 8 years' time, this will be reduced to 0. I don't think this is going to happen. So how do we achieve net zero if we still need natural gas purchases to heat our buildings? That's kind of the big question behind that net zero carbon ambition of the university. I think we can easily get rid of the electricity linked emissions, but emissions linked to the power we need to heat the buildings is much more challenging. So one way of getting rid of these remaining emissions, say from the purchase of natural gas, is by offsetting. So net zero means that the greenhouse gas emissions that we release as a university are counterbalanced by the removal of greenhouse gas from the atmosphere. So that's the topic of my talk today. How can we, if by 2030, in 8 years' time, we still use fossil fuel, such as natural gas, how can we counterbalance this consumption and offset some of the emissions that remain by 2030? Now, even the head of our sustainability team actually acknowledges that they will have to offset some of the emissions that remain by 2030. But the question is, how do you do that? Now, I wrote this opinion piece. It's just 1 page, and you can read it online. It's a summary of my thinking behind this. So my argument is that universities, they own a lot of land in the United Kingdom. So if you look at the land ownership of Oxford and Cambridge, it's enormous. So Oxford is the biggest landholder in the United Kingdom. They have a lot of rural land, they have farms, they have inherited, estates, and they all belong to Oxford. So my argument is that universities should use the land that they own themselves to offset their carbon emissions, rather than paying someone else to offset emissions for the university. Now, we looked at the carbon management plans of universities, of 16 universities in the United Kingdom and in the United States, but not a single carbon management plan was talking about the land that universities own, how they manage that land, and how they could use that land for carbon offsetting. Now, Newcastle University owns and manages two research farms. So here's Newcastle. We've got a farm at Cockle Park, and we've got another farm, it's called Nafferton Farm. So these farms are quite substantial. So this is the size in hectares. And, we control the way these farms are being managed. So my research question is, can we do something at these farms to see whether we can use them for offsetting carbon emissions? And why is this very important? Because about 40% of all the greenhouse gases in the atmosphere resulted from agricultural activities and the conversion of land use. So this is actually more important than the emissions from the combustion of fossil fuels. So if we have a lot of land that we manage, we really need to start thinking about what does this land management mean for greenhouse gas emissions, and how can we maybe change the management of the land to offset some of the emissions that we have from the use of fossil fuels. Now, carbon offsetting is actually very controversial. So this is an image I took on the trip with my colleagues here at KMUTT, a picture of a nice rainforest with the greenery, and you can see that this type of ecosystem has a lot of carbon storage. So one way of how you could offset emissions is by preserving rainforests. So we also saw on our trip how a lot of this woodland is being cut down in Thailand at the moment. So you can convert it into rubber plantations or coconut tree farms, or you can see conversion into other types of agricultural usage. So that will release carbon into the atmosphere. So often in the United Kingdom or in Europe, we would like to pay, say, communities in Brazil or maybe in Thailand to stop cutting down rainforests so that the carbon in these ecosystems can be preserved. But I don't like this approach, because it basically means that we, just using our money, are externalizing all the conflicts that relate to restricting land use. So there's a good reason why people might want to convert forested land into agricultural land, because it provides economic opportunity, or it provides food production, and so forth. So we can't just think about carbon storage in isolation. We also need to think about why people would want to change the land use and what's their motivation. So what I would like to show today is that we don't need to do this carbon offsetting by paying people in Brazil or paying people in Thailand or in Malaysia. We can actually do this using our own land. And that will mean that all of these conflicts that relate to carbon offsetting, we will internalize them and bring them within the institution. So universities in the United Kingdom, we own a lot of land, and we could use that land for carbon offsetting if we don't reach net zero by just cutting emissions. Okay, so what about the methods? So my hypothesis was that Newcastle University could offset a significant amount of its scope 1 and 2 carbon emissions by changing the land use at its 2 research farms. So here was our method. First, we needed to know how much carbon we have at the research farms. And to do this, we considered the carbon in the soil, and we considered the carbon in the trees. So we would take soil cores at different locations and measure the amount of carbon in the soil. And we would also determine how many trees we have and how much carbon is stored in the trees. So this will give us the carbon in the soil, and it will give us the carbon in the tree. And then we can analyze how the amount of carbon changes for different types of land use. So we can look at our land use records and can compare the amount of carbon per hectare with the type of land use. And we can do some statistical analysis to see if there's a link between the amount of carbon per hectare and the way we manage the land. We can also look at historical records to see if the amount, or to see if there's been a change in the way we've managed our land. And this will allow us to predict past, current, and future carbon storage at our university farms as a function of the land use. And then in the third step, we can use this data and we can see, okay, well, how many emissions do we have? How much do we need to offset? Or now, what's the emissions currently? What's the current carbon in our university farms? That's the baseline. And then we can set some reduction targets. Say we want to offset 10, 20, 30% of emissions. And then we can predict, if we change the land use, how much carbon will we have at our university farms. And this will allow us to define realistic carbon offsetting plans. So that's the approach we took. First, we survey carbon. We establish how much carbon is at our university farms today. And then we see how this depends on the land use. And finally, we develop some scenarios. If we change the land use, how can we change the amount of carbon that we have at our university farms? So to do this, we took soil cores to 90 centimeters, and we did 3 different sections to measure the soil carbon for the topsoil, and then 30 to 60 centimeters and 60 to 90 centimeters. Also, we looked at trial plots within our forests. How many trees do we have? And what's the diameter of the tree at breast height? And how high is the tree? So this allows us to quantify how much carbon is stored in the trees. So this is the soil collection. So you can see here, this is one of our farms, Focal Park Farms. So I had a very good student. She took a lot of soil cores, and we took it with tractor-mounted equipment because it's not so easy to drill. But you see there's 50 soil cores here, and there's some, I don't know, 47 soil cores at the other farm. And we do it across all of the fields and also in the woodlands. So these are the woodlands here. And here we've got some woodland here. So we take the soil core and we do 3 sections: topsoil 60 to 30 to 60 centimeters and 60 to 90 centimeters. And then for the woodland, we have some trial areas with different tree species. So we determine what type of species we've got. we determine what we call the diameter at breast height. So that's just about as high as you can reach. How thick is the tree and how tall is the tree? And we also need to know what's the coverage of the land area with trees, we call Canopy Coverage. And there's a software tool that you can use online, it's free, that will calculate the amount of carbon in your land if you provide this type of information. So it's called i3 Tools, i3 Echo, and is a tool that has been developed by American scientists. You can download it on your mobile phone and you can use this, very convenient. Okay, so once we knew the land use, we could compare and how much carbon we have, we could compare the past with the present. So here I show you, for example, at Nefferton Farm, where the woodland is. So you can see that the woodland here, is only in the steep, inaccessible part of the land. And that goes back more than 1,000 years. So over 1,000 years ago, when the farmers wanted to have fields, they would cut the trees and they would convert the land into agricultural land. So that happened in medieval times, so over 1,000 years ago. And you can see that there's barely any trees in the fields. So all of this flat land is bare of trees. And we only have trees in what we call the deans. So in the steep slopes, you cannot do agriculture. That's where we've got forest left. So this medieval practice of woodland clearing for agriculture left woodland only in the most inaccessible locations, including at our farm. So at Nefferton Farm, we've got ancient woodland, but only in this kind of in the dean, so in the steep, hilly terrain. Another thing that's interesting about Nefferton Farm is that for quite a while we compared conventional with organic agriculture. So the farm is like split in two, and one half of the farm is managed conventionally with pesticides and inorganic fertilizer and so forth. But the other half of the farm is managed organically. So this part of the land has always been under organic management for about 14 years. So we can check whether this management practice has an impact on carbon in soil. This is a map of Cockle Park Farm from more than 100 years ago, land use more than 100 years ago. And what's interesting is that at the time, most of the land use was pastures and meadows. So that means grassland for the cows and the cattle. And there was only 16% in yellow here for growing wheat and cereal. So most of the land was actually grassland and only 16% was for crops like wheat, oat, and so forth. Now that has changed a lot. So nowadays, we have a few fields that are still permanent grassland, but most of the fields are under what we call crop rotation. So these fields are being plowed or tilled almost every year. And that means that, that typically is not good for carbon in the soil. So at Cockle Park Farm, we could see the effect of managing land as grassland versus tilled arable land. You can also see that on this map here that there was some tree plantation a long time ago, about 100 years ago. So we could compare this relatively recent woodland with the older woodland up here that has been here since thousands of years ago. Okay. So these are the types of land use we can compare at our university farms: agricultural versus woodland. We can also compare broadleaf woodland versus coniferous woodland. So coniferous woodland means woodland with needles, and broadleaf would be with big leaves that are normally dropped each year. So coniferous woodland would be pine trees, for example. We were able to compare recently established with ancient woodland and pastures grassland with arable fields, and conventional versus organic management. And once we understood how land use impacts on carbon, we were able to develop some scenarios like, what if we change the land use? What if we plant more trees? And these trees will grow and accumulate carbon. How much of the carbon emissions from the university can we offset by changing the land use? So every year, based on current rates, the university emits about 6,406 tons of carbon per year. So we are asking how much of this could we potentially capture in the biomass in the soil at the university farms. So that's the methods. And now we can move on to the results. So first of all, we quantified the baseline. How much carbon is at the university farms today? And it's about the total carbon store is 100,000 tons. That's 16 years worth of emissions from the university. So you can already see that this is actually relevant because it's not an inconsequential amount. So there's a large amount of carbon in the land. And if we can increase the amount of carbon in the land, we can potentially offset some of the carbon emissions. Now, currently, most of the carbon is actually in the agricultural land. And a small amount is in the woodland trees, and in some of these hedgerow trees. But the reason why most of the carbon is in agricultural land is because most of the land is actually being used for agriculture. So this plot is a little bit misleading. We should ask, what is the storage per hectare rather than what's the total carbon storage? So this is from our analysis of the soil carbon. So we find that in woodland, you have significantly higher amount of carbon in the soil of woodland as compared to agricultural land. So if you convert woodland to agriculture, you don't only lose the carbon in the trees, you also lose carbon in the soil. That's what we find from these data. There was no significant difference between the very old woodland and the woodland that was planted 100 years ago. There was no significant difference between broadleaf and coniferous woodland in the soil. There was a significant difference between permanent grassland and arable land. So if you have grass, if you have pastures and meadows, you have more carbon in the soil than if you have agricultural land, arable land. There was no significant difference between organic and conventional measurement. So this basically simplifies the system a lot. So there's only two things that matter. One is whether it's woodland or agricultural land, and the other thing that matters is whether it's pasture or arable land. Everything else is only a small difference. So this is the most important slide. This is basically, everything is on this slide that you need to understand, okay? So this shows carbon storage per square meter. So arable land, the land that is being plowed, you have about 12 kilograms of carbon per square meter in the top 90 centimeters of soil. If you manage this land as permanent grassland, you have significantly more carbon. So pastures, meadows have more carbon than arable land. And that makes sense because every time you plow, every time you turn over the soil, you're stimulating the soil bacteria, you're losing carbon. But the really big difference is between woodland and agricultural land. Because in woodland, not only do you have more carbon in the soil than in the arable land, you also have carbon in the trees. So there's a huge difference per square meter between carbon in woodland and carbon in the agricultural land. So this is the amount of carbon per square meter for different types of land use. And this is how we currently manage our land at the university farms. So you can see that unfortunately, most of our land is arable, which has the lowest amount of carbon. And we have the least amount of woodland, which has the highest amount of carbon. So the way we manage our farms is very, very poor for carbon. We do the wrong thing. We have the wrong type of land use. We have agricultural land use, especially arable land use, and that means we don't have a lot of carbon in the land. So if we want to change the amount of carbon in our university farms, we need to convert some of the arable land into grassland, or even better, some of the agricultural land into woodland. And then we can capture a lot of carbon. So that's really the only way of how you can make a difference. Okay. So here's what you could do by changing land use at our university farms. If we went extreme, the most extreme thing we could do was to convert both farms into coniferous woodland. And if we did this, we could offset 50% of our emissions for a period of 40 years. So that shows that if we want to do this, we can make a huge difference. We can offset half of our emissions just by converting our farms into woodland. Now, maybe this is too extreme. Maybe we want to keep some agriculture at our research farms. So how about converting one of the farms into a carbon capture research center, just one of the farms? And we allow rewilding, we let the trees grow, mixed coniferous and broadleaf woodland. Then we can still offset 30% of our current carbon emissions for a period of 40 years. So again, this is very, very substantial, the amount of carbon that we could potentially capture by letting one of our farms convert into woodland. If we change the land use back to how it used to be 100 years ago, with more grassland and less arable fields, we could offset 64% of our emissions, but for a shorter period of time, 5 years. And if we just want to offset 10% of our emissions, then this is a type of land use that would be consistent with this reduction target. So we had all these results, and I show it to our farm manager, and I say, how about converting one of the farms into woodland? And he wasn't very happy at all with this proposal. So he said, well, wait a second. We've got some agreements, tenancy agreements, and we cannot plant trees at our farms. It's legally not possible. Also, he was concerned that he would lose subsidies for the farms and the tax status, so lose money if we convert our agriculture into woodland. And also he mentioned that there's a conflict between this carbon offsetting and food production. So he prefers to use the land for producing food rather than offsetting carbon emissions. So the farm manager would rather change land use in a way that is consistent with agriculture. And he mentioned like plowing less or recycling straw and manure, or there's a technique, it's called mob grazing. They have a lot of cattle on a very small space, and he says that's good for carbon capture in the soil. But he doesn't really have any data to show that this would make a difference. We also looked at other options, such as planting more tree on the university campus instead of at the university farms. But that would only offset 1% of our emissions, even if we converted all of our sports fields and all of our green space into woodland. So you can forget about it. It's nice to plant trees on campus, but it doesn't really make a difference to your carbon capture. There's just not enough trees that you can plant. Also, there was a site redevelopment recently at a place called Newcastle Helix. So we said, how about you add 3% biochar to this blue-green space if you're redeveloping the site. But this would only offset 11% of our emissions for only 1 year. So again, it's a nice idea, but it's not really going to make a difference for carbon offsetting. So this brings me to my conclusions then. First of all, we showed very clearly if the university wants to use its land for carbon offsetting, it can do it. And there's a huge potential. The university can offset up to 50% of its current emissions over a period of 40 years by changing land use at its research farms. However, the only effective way of doing this is by letting woodland grow where we currently do agriculture. So if you convert an agricultural field into woodland, you increase the amount of carbon in the soil, but also you increase the amount of carbon that's in the biomass. So this is the most effective way of capturing carbon in your land. However, there are major concerns from stakeholders about giving up agriculture, and they're very reluctant to move to forestry. My counter-argument is that any other idea that people have about offsetting carbon is not effective. If you want to do it on the university land, planting trees on campus, using biochar, all of these ideas, they're nice, but they're not effective in offsetting carbon emissions because they will only make a very small difference. So I would say in 8 years' time, when the university will realize it cannot stop using all of its fossil fuels and it needs to offset some of its emissions, I think the university should be serious about using its own land for carbon offsetting rather than paying someone else for carbon offsetting. Because you can see that carbon offsetting is very controversial. There's land use conflict. The farmer would rather use this land for agriculture rather than planting trees. But this same conflict will also be in Brazil or in Malaysia or whatever you do your offsetting. Is the same conflict. So it's actually better to try and have this within the institutions and try and use your own land for offsetting so that you can have these discussions and own the conflict as an institution rather than try to export the conflict. So here's the person who did all the hard work. So this is my PhD student. She did a lot of the measurements, but I also took some of the soil cores. I actually damaged my shoulders doing this and had a lot of pain later. So hopefully this will pay off. But if you want to read the details of this study, this is the publication. And yes, let me know if you have any questions.
Thank you very much, Professor Werner, for the very clear and interesting work to offset carbon emission by the own land of university. So I think this is a very good example for the KMUTT, because we also have our own, we call it the forest in Ratchaburi campus. Is around 1,000 rice. Yeah. So, and also, yeah, we also plan to plant the mangrove for another 100 rice or something. Yes. Okay. So now the floor is open for audience. If you have any questions to the professor, you may raise your hand, or you just turn on your camera and microphone and ask the question. I have a few questions though, but maybe let others ask first. Okay, maybe people are still digesting about your presentation. So I have a question on the when you explain about offsetting by different scenarios on the page 31, and is it assumed that during the time of the offsetting, the plant is still at the stage of growing? I mean, before it's reached the maturation. Yeah, because this is also our question before that in the Ratchaburi forest that we have, and now it's already about 20 years old. So we don't know when, because when it's getting very old, the trees, we think that it might start to absorb less or not in the trend that we estimate. Yeah.
Yes, that's a very good question, and you're absolutely right that at some point your forest will reach maturity and equilibrium, and at that point there will be no capture of carbon. So the way we did the calculation was we assume it takes 40 years for the trees to reach this mature state, because that's the average age of the trees in the woodlands that we investigated. So we say for that time period between now and until we have a mature woodland, that's when we can capture and offset emissions. That's why I say for a period of 40 years. I think it just buys the university time to adapt its power use and things like that. Okay, I see. Yeah, I agree with that. And also on page 33 that you mentioned about biochar, I think is very interesting. And I think that there have been a lot of studies in Thailand, but I don't think that any have done this kind of calculation. And when you mentioned that it's can offset for only 1 year, but if we keep doing as like we can offset every year, right? Okay. Yes, you're right. So I could give a different presentation on the biochar. So the idea there was, this is urban land. So, you know, in agricultural land, maybe the farmer can apply biochar each year and plow it in. But in an urban development, our idea was when the construction happens, that's basically when you can add the biochar. But later it will be difficult because you cannot really dig up the soil anymore. Yeah, so the idea was you do it just one time, and then then it's not very significant. But you are right, you could apply it every year.
Yeah.
But the challenge would be, how can you produce enough biochar? I don't think you can produce enough biochar for the university to offset your emissions. So it would be a very big operation.
Yes.
Yeah.
Okay. So my last question, which is not about the university, but we got some questions from farmers, and for example, they grow the coconut trees, and their question is whether by keeping the land for coconut trees, it can be converted into some kind of carbon credit, so that it add the income to the farmers, so that the farmer don't sell their land for the for the housing companies to make condominium or some houses. Do you have any suggestion on that?
Yes, I think it's actually a huge opportunity. I think people who want to make money, they need to start thinking about these things. Because I'm sure when we reach that year of net zero, every institution will realize they have to offset. Because I don't think a single institution will be able to go down to zero fossil fuel usage. And then they will have to pay someone to offset that carbon. So if you can offer them a solution, if you offer our sustainability manager a solution, you say, I manage my land to increase carbon, and here's the evidence, he will give you money, I'm sure. That's the easiest way for our university to offset our emissions. Now, I'm not a fan. I tell the university, don't do it overseas, because you don't know what kind of trouble you're causing there, right?
Yes.
There's lots of people selling you things. You don't know how it works. You should do it yourself. You have lots and lots of land. Universities in the United Kingdom have a lot of land. Do it yourself. And then all these questions, how much carbon are you actually storing? How do you do it? What's the trade-off with food production, with income from agriculture? All of these conflicts you will have yourself. And I think that's the honest way of doing it. Like KMUTT, you use your own land, and Newcastle, we use our own land. And don't just pay someone and you don't have control over what they're doing.
Yeah, I agree. And university as a non-profit organization, we don't have so much money to pay anyway. Yeah.
But
Okay.
I'm sure that it will be a huge market. It will be, carbon offsetting will be a huge market in 5-10 years' time. Every institution that is serious about net zero will have to buy carbon credits.
Yeah. Okay. Okay. So if anybody have any question, you can just ask, because I might not see whether any hand raised. So meanwhile, can I ask? Okay, I saw Sohail. Okay, yes, please. You just turn on your microphone, yes, and ask question. You can introduce yourself as well.
Yes, first of all, thank you very much. Okay. What's that problem?
Well, I think that there should be only one microphone in the room. Otherwise, it will have the echoing. We cannot hear you, Sohail. We cannot hear you.
Have been planted or have been used in that woodland and other areas, because there have been number of research being going on and have been conducted in the past. Like there are certain species of the trees which capture more carbon compared to the other species. So maybe just a question and also a comment, like in this research, have we considered about those species, or just we have done the evaluation of the current species that have been found in different areas of 2 farms that you have mentioned in research? And the comment is, like mostly in England, they use English oak wood, and around 36% of the total trees in UK are using, consist of English oak wood. But there are other species which capture more carbon, like yellow maple. So are we going to consider that approach as well to, use yellow maple more compared to the conventional trees we use to capture more carbon, so that we don't disturb the agriculture farms, because the food security is also a major concern, because right now there are some political conflicts and wars going on in the world. So if we're gonna go for the carbon neutrality, so are we going to look for this option or not? Thank you very much.
Okay, yes, thank you. Another very good question. Let's just maybe go back to this publication. Okay, sorry. That didn't work. Yes, so on this slide, you can see that we look at different tree species. So larch is a needle tree, coniferous tree. Sycamore is an imported coniferous tree. Norway spruce is another coniferous tree. And then here you've got oak, which you mentioned, and Sitka we also have. So we did look at differences between different types of trees, and there is a difference. Like coniferous trees are better at capturing carbon, but it's a small difference. So if you go here, you know, these are the broadleaf trees like the oaks, and this is the coniferous tree like pine trees. Now, people don't really like us to just plant these type of trees because of biodiversity is not very good. You know, that's another question, biodiversity and all of that. But my point is, the selection of tree species is just a small question. It's not a big difference. What really matters is woodland or arable land. That's the big difference, right? I'm an engineer, you know, and I do numbers. And a lot of this research is done by natural scientists. And they are just saying, oh, I planted different tree species. and maybe make a small difference, but doesn't make a big difference. And the reason is because the solar energy that the tree uses to grow is basically the same. So basically, the amount of energy that trees can use per square meter is roughly the same. So I don't think that species will make a huge difference, species selection, but you're absolutely right that we need to consider these trade-offs between biodiversity, native versus invasive species. I mean, some people want to plant elephant tree, like I saw on my elephant grass, like I saw on our field trip. But elephant grass is not native to the United Kingdom. So, you know, you need to find an optimum that kind of considers a range of aspects, not just carbon capture. I completely agree with this. But I think if you do it on your own land, just to say it one more time, if you do it on your own land, all these conflicts, you can have these discussions. We have very good biologists in the university that can do biodiversity surveys. So why not one of our farms, we try out all of these different options and use it to do the research and find out what's the benefit, what's the cost, what's the best way of doing it? So that would be my argument. Does that answer your question?
Okay, so any other questions? It can be questions or it can be the point for discussions as well. Because I think some of the people here also studied about the soil carbon.
No questions, that's fine. If you want to have one takeaway message, it's really this slide here, you know, and this is for me as an engineer. You know, you can do many different things, but at the end of the day, if you're serious about offsetting, most of these things will not really be sufficient to make a difference. The only thing that really will make a difference is if you move from arable land to woodland. Or maybe in the United Kingdom, we can also think about wetlands. So we have peatland, store a lot of carbon. How can we preserve or maybe restore peatland? I think these are the two options that will make a difference for offsetting. And I think everything else that people talk about, selecting species and, you know, planting more trees on the campus, things like this is not really going to be sufficient for offsetting.
Yes. Okay. อาจารย์สุชัญญาค่ะ You may turn on your microphone.
I'm not sure if in online we soon can hear my voice, but I would like to ask, for example, I read your slide, for example, about the method to estimate like the carbon dioxide emission from the land use, for example. I would like to ask for your suggestion, for example, like how do you calculate, for example, like I see your slide number 30 like this. Like for example, a different type of the plants. It show different portion of carbon storage, something like that. So can I kindly ask your suggestion how to use or which program you use to get, for example, there any specific program to calculate like carbon dioxide emission, something like that? Thank you very much.
Yes, thank you for that question. So for the soil, we had these sampling points, and then we use kriging, like interpolation, to estimate carbon in between the points. And then you can estimate on average per square meter how much carbon you have. Do you understand that? So we have some points, and then you can interpolate in between and estimate how much carbon you have in these fields. For the trees, we use this software here. You can click on it and go online. It's very helpful. So this is the information you need to enter, like which species, the diameter at crest height, you measure with a tape, and then how high the tree is. There's some little instrument you can measure how high the tree. And then from satellite, or we have this drone image. If you have image like this, the software can estimate. We call Canopy Coverage, like how much of the land area is tree. Yeah, so this is the other tool that we use. And then this switches the some of it we just did in Excel. So for the scenarios. Maybe I can show you. Sometimes it's easier to show the so here we just know how much carbon you have per square meter for different types of land use. So grassland, arable land, woodland, coniferous, broadleaf. And then this is for the biomass, the tree. And then here you've got how many hectares you have of each of these. And then, you just multiply, and that gives you this amount of carbon. So here it's all coniferous woodland. So that's why it's all in this line here. So you've got the carbon in the soil, and this is the carbon in the woodland trees. And then this scenario here, is a different one. So you can just change these numbers, how much land you want to have with which type of land use. And this will stay the same here. So this is from the experiment. Does that make sense? And then we calculate, we divide by 40. So we think, it takes 40 years for the tree to grow. So in each year, this is the total difference. And then we divide by 40. So each year you can offset this much by letting the trees grow and things accumulate. So let's see which university reaches net zero by 2040, whether it's KMUTT or Newcastle. But I'm very skeptical. You know, you look at these videos on YouTube and yeah, there's some solar panels on the roof, but I don't think they will achieve it personally.
Yeah. In fact, we made a plan for the pathway to carbon neutral in 2040 for KMUTT, and I mean with the measures on RE, EE, and zero waste, we could reach only 30% reduction, but the rest we rely on our forest. Yeah, but we use the different way of estimating the carbon absorption. So we by one of the senior researchers here, they use a tower to measure the net carbon emission.
So you measure concentration in the atmosphere?
Yes, yes, above the canopy, as a representative for the forest. So, and it's average daily, and also we accumulate for years. Yeah, and that's why I asked you one question about the trees that reach their mature age. Yeah, so in that study, they predict that it will reach the peak at around sometime before 2040, and after that the absorption is getting lower.
Yeah.
Yeah.
I mean, of course, you could cut down the tree and use as biofuel if you want, and plant it to one. I mean, it's possible.
Yes,
Also,
yes, yes.
yeah.
And in general, do you think the short rotation short rotation trees like elephant grass or lucina, which we can cut within 3 to 5 years, compared to teak wood and oak wood or other thing, do you think it makes a difference in the soil carbon? Because when we grow the energy crops like short rotation plants, people keep saying that it will damage the soil. Not particular the carbon, but everything, all the nutrition in the soil. Yeah, like especially the eucalyptus. Yeah, and that I think is still an argument whether it's really make the soil quality worse. Yeah.
Yeah, it's another good question. I mean, the only thing we see is if you break up the soil, if you plow it, that's when it releases carbon. That's very obvious. That's why the arable land, the tilled field, has less carbon than the woodland. If you just keep it as grassland, it also has more carbon. So I think that's the main question, if you break it up or not. But maybe nutrients, yes, of course, it might also have an influence. I mean, the other question is, what about the other greenhouse gases? I haven't looked at it, you know, nitrous oxide or methane.
Yes,
yeah,
yes,
the real world is very complicated.
Yes, okay. Yeah. Yeah. Okay.
In peatland, for example, maybe they release methane, you know.
Yeah.
Yeah.
Do we have more questions from audience? Okay, Dr. Natapong, would you like to ask?
Yes. Actually, I'm not sure I should ask this question or not because it might be relevant to the topic for today. But actually, I am interested the slide number 7. You show the slide of the Newcastle University emission. It has scope 1 and scope 2. But the interesting is if you see for the last 5 years, the emission is reduced rapidly. Can you see? And my question is, what is the strategic or the measure to reduce the emission in Newcastle University? Maybe you have some idea what is the strategic to reduce the CO2 emission? Thank you.
Yes, thank you. So if I understand correctly, your question is about kind of this slide here, like how we are going to further reduce these emissions.
Yes.
Yeah. I mean, I think that's the problem with all of these announcements and so forth. The initial cutting is easy and the future cutting is difficult. Yeah. So here for electricity, there's many ways of generating electricity nowadays with renewable energy. So I think this is the easy bit. Yeah. And you can see they achieve a big reduction in grid electricity carbon emissions.
Okay.
And that's partially because the United Kingdom has more wind power now. It has more solar power. So the electricity you're buying automatically will have less emissions now than it had 10 years ago.
Okay.
But you can also, and the university is doing this, put solar panel on the roof, and you could buy a green tariff, so all your electricity is renewable. So I think getting rid of the orange color here is very easy. Yeah.
Yes.
The challenge is the blue. You see that there's no change here.
Yeah, yeah.
Yeah.
Yes.
What is this blue color? It's the gas we buy for heating the buildings. Heating.
Yes. Yes.
If you want to change the heating system in an old building, you have to replace everything. It's not possible.
Yeah. Mm-hmm.
So this is the challenge. And I'm not sure how they are going to sort this out.
Mm-hmm.
I mean, one thing could be my office is single glazed. You know, they could insulate buildings a little bit better. I think that would make a difference.
Mm-hmm.
Or they could try and switch from natural gas to biomass for power generation or heat generation, like you do in Thailand. You have a lot of biomass-fired power stations. But there's also a disadvantage which is air pollution. So natural gas is very clean, and if you switch to switch to biomass, you have more air pollution. So I don't know the answer here. I think this is the tricky bit, and maybe try to use less heat from the buildings, insulation, things like this maybe will help. But I believe this is where they need to use offsetting. I'm sure there's still going to be a little bit of blue left in 8 years' time. I don't see this go away by 2030. I don't know how they want to do this. So if you have an idea, let me know. But I think this is the tricky bit. Yeah, not easy.
Yeah, yeah. Yes, yes, I got it. Thank you very much.
And of course, you may know that the price for gas is going up, because of the war in Russia. So it's not just the environment, it's also saving money. But this is a tricky one to try and address. Thank you.
Okay.
Thank you.
Okay, thank you very much, Professor, and thanks for all the audience. Okay, so I think we we had a very fruitful sessions. Yeah. And okay, so yeah, I've heard that the professor will return to UK this Friday. So, but anyway, we might meet on Thursday for a trip to Ratchaburi.
Very nice. Yes,
Yeah.
thank you.
Okay, thank you very much. And before we stop, I would like to just say to the audience that for the record of the webinar, you can find it on the website or the Facebook of the KMUTT. It will be launched soon. So now we already have 4 webinars, so you can watch it later. Okay, and please stay tuned for the next webinars in the series. Okay, so thank you very much again, Professor, and everybody have a nice afternoon. Thank you. Bye-bye.
Thank you. Bye-bye.